So our special guest, Andrew Ruff, was here virtually with us a year ago when he generously offered to lecture at the start of the 4B Comprehensive Building Design Studio, shaping the way we thought about carbon and materials throughout the term. Andrew Ruff is the research director at Gray Organschi Architecture and the Timber City Research Initiative, where he focuses on developing a comprehensive approach for incorporating timber construction into cities, an approach which simultaneously addresses regional material flows, economies of carbon generation and sequestration, and the development of new industrial processes, and the complex spatial, architectural, legal, and logistical challenges of constructing timber buildings in dense urban centers. He previously held appointments as critic at the Yale School of Architecture, visiting assistant professor at Wesleyan University, and lecturer at Georgia Institute of Technology, and served as part of the guest faculty at Roger Williams School of Architecture, Art, and Historic Preservation, where he led design research into the applications of mass timber assemblies in mid-rise building applications. In addition to his professional degree in architecture from the University of Tennessee, Andrew holds a Master of Environmental Design from the Yale School of Architecture, and he has lectured and published on the subject of mass timber buildings in the global carbon economy. Andrew has been with us for most of the day, and he offered a seminar for grad students this afternoon. We're delighted that Andrew could speak with us today and in person to wrap up this lecture series. So welcome, Andrew.
Hi, everyone. Thanks so much for having me. Jalia, thank you for your hospitality, both virtually before and in person now. I'm thrilled to be here, actually in Cambridge. I was telling some folks earlier, I very much appreciate the pizza bribe for you to attend. I'm in full support. Students should be fed. So it is dark. It is cozy. You are satiated with pizza. I will try my best not to put you to sleep. Fair warning, I do have some graphs. So I will supplant that with hopefully some compelling pictures of buildings that our office has designed and built over the past couple of decades. And really hope to talk through kind of our approach to the built environment and its role in what we think is a really important relationship between carbon, construction, and the way in which we inhabit the Earth. So we'll start here. This is Tokyo, city of about 41 million people, the same population as Canada, in 0.02% of the same land area. That in of itself is interesting, but perhaps more interesting in the context of the built environments is that this is the densest aggregation of man-made material on Earth. And so this is a stockpile that we as humanity have designed and built over the course of generations, and is really a pretty arresting artifact of our anthropogenic way in which we build. And the approach to urbanism, as we kind of conventionally have conceived it, is that while it offers efficiency in certain ways, it also comes with a whole host of unexpected challenges to our environment, the way in which we inhabit these places as humans, and our impacts on immediate and far afield ecologies. And this problem is really only getting worse. And so these are just a whole host of numbers that look at what does it look like for global urbanization, the built environment, over the next 25 years. And so we're going to be adding 2.5 billion people to the urban population. That's 2 times the global construction footprint of what we have currently. It's a building, 159,000 square kilometers, which is an almost meaningless number. It's larger than the size of New York State as a single building. $375 trillion of construction. And if we build this amount of building, which will be required to house the projected number of new urban occupants, we will deplete the entire global carbon budget for 2 degrees Celsius by 2040. So this is The reality of the built environment is that it is an enormous climate forcing, and it is only accelerating. I mean, with the COP30 going on right now, a lot of our colleagues in climate research have been publishing some relatively harrowing statistics as to where we stand currently. And in regards to this last number, our projected parts per million CO2 concentration, and which industries and which entities will be really responsible for shaping the future. And it is the construction sector, by and large, that is going to be the dominant force in our carbon footprint moving forward for the next, certainly for the next few decades. Of course, this is an architecture school, we typically don't think about the globe as our scope of work. We typically think about the building, and we think about the, whatever is inside of that exterior envelope and everything inside. And so as a profession, that is kind of how we've been trained traditionally, from a licensing and insurance and liability. That is our purview. But in reality, we as architects and designers of the built environments, we really need to think about these broader carbon flows and how our work in designing individual buildings and landscapes has impacts on further field issues. So looking at the carbon flows of energy that are required to heat and cool and power our buildings, looking at the carbon flows of constructed products that we are sourcing to build and fit out those buildings. And then finally, the carbon flows at the end of that building's life. And so where is that material going? Where is it? How is it being treated? And what is its second and tertiary life after the building? So that is really, from our perspective, this is the purview of the designer, is everything on this board. We are delivering buildings, but we are impacting and inflecting these enormous supply chains that reverberate around the world. And maybe we're not industrialists developing new concrete mixes, but the way in which we design and specify buildings has a really significant impact in how those industries evolve. What I do want to focus on, though, is not necessarily the heating, cooling, and powering of buildings. That's a kind of a separate discussion. But really what's important are these two phases. So the materials that we are using to build our buildings, and then what happens at the end of the building's life. And those two factors, and primarily the materials we put in our buildings, will account for approximately half of the building sector emissions by 2050. So it's not the case that sustainability means really efficient heating and cooling and good insulation and air tightness and all the things that for the past 25 years maybe we've been really focused on. Now that we have advanced a lot of those topics, we're really looking at drawing down the embodied carbon and finding out solutions not only to minimize carbon, but actually to create carbon stores in the built environment. And so as I was in the school earlier today, I could, was picking up on certain conversations. I heard the word carbon. I heard the words LCA frequently. All of the graduate students who I spoke to earlier were all interested in wood construction. So I feel like maybe I have selective hearing, or maybe we're amongst friends here. So I will quickly go through some of these things, which I think are very much in the water here at the University of Waterloo. So I'll be fast. And so really what we're looking at as designers are these embodied emissions separate from operational emissions. And what does that include? That includes the transportation of materials from their sites of extraction to production to the building. It includes the actual means and methods of assembly and bringing those buildings into the built environment. Over the course of the building, it includes how we replace materials, the duration of which we replace them, off-gassing from those individual elements and components. At the end of the building's life, it's actually taking the building apart. So ideally, we're saying disassembly, not demolition. And then once you've disassembled a building, how do you recover it to preserve that value and that embodied carbon for lives beyond the building that you designed? And to put a really fine point on it, we'll look at those kind of what are the relative carbon impacts of all those different activities. And so if we take those discrete phases, and so these are the LCA phases that maybe you have all taken as a seminar course, or maybe it's a mandatory curriculum here at the school. And we look at, this is conventionally how those LCA stages are shown, is that we have a spike in production. You have some relatively minimal carbon expenditure to actually build the building. And then the kind of the gorilla in the room is operation. And so heating, cooling, operating building, that's the one, if we look at this graph, that we need to solve. Well, what if we make a really efficient building though? So what if we build a passive house? all of a sudden that becomes a much less critical problem to solve. And all of a sudden, the production is the largest single embodied carbon in the building. And then what if we build that out of a carbon storing material? Can we draw that down? Could we actually have that become a carbon storage? So these are kind of levers that we're interested in pulling on as designers to really impact the life of the building. And what I think is really important to think about is the temporality of this. And so all of these impacts exist over the life of the building, which we would, in an ideal world, like to be 60 years. Certainly, that's what how the insurance market conventionally defines it. And so if we assume that the life of the building is 60 years, when do we accrue all those carbon impacts? And so when we build a building, we source all the materials. It's a huge carbon spike. In those first 18 months of a building, it accrues this really significant carbon debt. And then as the building is lived in, it's maintained, it's restored, you have these intermittent carbon spikes, maybe every decade, every 2 decades, the flooring's replaced, you get a new refrigerator, you change out the roof. And then finally, at the end of the building's useful life, there's a spike in the energy and emissions required to actually demolish and perhaps recycle the building or take it to a landfill, incinerate it. So that's conventional embodied carbon, and that's where we see our timeline. And so that first year is incredibly important to identify how to avoid those embodied carbon emissions. If we go with a material class that stores carbon, all of a sudden we're starting from a negative. We're able to store a significant amount of carbon at the outset, and that line of accrual really changes. And then when we compound that with looking at the operational carbon and seeing where those two intersect, I think this is where we're very focused on as a practice in finding these opportunities between building stored carbon, lowered emissions for operations. If we go to a passive house level building and we're able to avoid a significant amount of emissions with conventional construction. It doesn't take that much more carbon to build a passive house building, it just takes better design and better construction. But if we build a passive house building with biogenic carbon storing materials, we double the amount of avoided emissions. And so the manner with which we build a building is just as important as the performance to which that building is designed. And it's all the more important, again, because of temporality. This assumes a 60-year lifespan of a building, and that carbon payback for conventional construction will occur in about 35 years. As opposed to a biogenic building, it'll be about 7 years. And that's really important because here in 2025, 35 years is a long time. It's a long time to assume a payback period, given what we know about the arc of global warming, climate change, and carbon emissions. And so the sooner we can act collectively as an industry and as a profession, the sooner we can have an impact on these really intense and quite horrifying realities that we will be facing in 25 years. Just to put a slightly finer point on it, looking at, this is kind of the business as usual. We're assuming no significant changes to the way in which we operate the building sector, the transportation sector. We've already missed 1.5C. We're probably going to miss 3C at this rate. If we pivot to transsectoral decarbonization, which is everyone kind of collectively looking at electrification, are looking at efficiency and sustainability, we can find opportunities to maybe rein this into 2.5C, which is kind of where we're thinking the trajectory is going. But then really, if we want to begin to bend that curve down, and so this is the critical part, is that we're going to overshoot it, but how fast can we get back down to a reasonable warming level, which is, again, a horrifying thing to say. We need negative emissions. And so how are we doing? There are some positive news. And so we look at global solar power growth, and every year the global production of solar energy is outstripping the projected volume by significant margins. In 5 years, this will double, and it'll double again and double again. Same curve is true for electric vehicles. So fantastic. We're seeing these kind of compounding acceleration of adoption and pivots in consumer energy appliances, vehicles. But in reality, when we look at the greenhouse gas emissions on our current pathway, it's still close to 2.5, 2.9 C. And the lived experience of us as humans is that it's getting increasingly uncomfortable. Perhaps less so in lovely Canada. South of the border, it's getting kind of toasty. And so we collectively are feeling that. And then as you all are no doubt aware, the things that we have taken for granted as a species, that forests are a carbon sink, those assumptions are being challenged by the reality of a warming planet. And so we're seeing more and more devastating wildfires. We're seeing more and more release of carbon into the atmosphere by forests. And how do we as designers react to that? And so again, this is the built environment status quo. This is kind of where we are, and this is how we've organized our collective building sector. And what we would like to do is to look at a decarbonized future. And so we look at eliminating waste, we improve circularity, we avoid extractive materials and mineral-based construction approaches, we eliminate hydrocarbons. So the goal here as an industry is to pivot towards electrification, efficiency, and circularity. So I'll just end there because I think I've solved it. No, but so what I do want to talk about, how do we get there, and how do we as a profession actually deal with this in reality, and where have our practice, where have we found success, where have we found challenges, and where do we think there's some opportunities? And so if we look at the idea of decarbonizing design, this is a drawing that myself and my co-authors on the carbon book we put together to try to chart, and this is not something to be interpreted. This is simply exercise in showing where do designers have agency. The building sector is an enormous machine of consumption and capital development, and architects per capita play a very small role in that. We do have the ability to kind of marshal through specification and design and reorient certain aspects of this industry. But where do we make an impact on that chart, from on the far left, in the initial stage of a project, and to the far right, handing over the building to the owner? And so the three areas that I want to focus on are the premise. And so identifying, is this a building that is needed? Should this be built on reclaimed landscape? Should this be built as an adaptive reuse project? Ensuring that there's a concord amongst the parties, the contractor, the owner, the engineers, the architect, that what is the goal of this project? And so is this project appropriate? That is a difficult conversation to have. A lot of times we as designers are brought in once a lot of those decisions are made. They know where the site is, they know what the program is, they know what the timeline of the budget is. But I think it's our responsibility to question some of those things and to bring that to the table, which is a reflex that we typically don't exercise because we want to build things. We're not in architecture school because we'd like to avoid building. We're here to design and to build. And so, but what we're designing and building is one of those important questions to ask. Then once we've arrived at kind of a concord of what the premise is, then we look at sufficiency and what is a sufficient building? What's a sufficient design? This looks at, what's the appropriate size of the building? How much of it do you need? What kind of volumetric implications are there? What do you need that building to do? Can you share spaces? Can you share program infrastructure? Can you combine your building with someone else's demands? So I think this questioning is looking at, not only are we building a building that is appropriate, but it's a building that's sufficient. Once we've answered all those questions, then we can talk about efficiency. Then we can talk about heating, cooling, making it airtight. But really, those three legs of the triangle all have to be answered. And if the first two questions aren't brought up, again, really as the agency of the designer to ask these questions, no matter how efficient the building performance is, you've neglected to answer kind of the fundamental premise of what is the building supposed to do. So I'll show a few examples of our experience with kind of trying to answer these questions. This is a project that we were asked to design by the United Nations as a demonstration for a residential prototype that could be deployed in disaster situations. And not only was that a performative goal, we had to keep residents cool or warm. We had to provide electricity, water, food, safety, security. But we also were tasked with embodying the UN Sustainable Development Goals, which are much more expansive and comprehensive than a conventional building brief. And so we as designers and also the builders of this really took that to heart and identified trying to map out all these various ecosystem services, performance goals, material demands onto this prototypical residential building. And so, if we look at premise, the premise was pretty clear. It's a small, efficient, shippable home that could be rapidly deployed. The sufficiency was that it had to have room for 4 people to live in it full time. And this is 220 square feet. I can't do the conversion to square meters. It is small. It is a very, very small footprint. And so thinking this is more as inhabitable furniture than a building was really the premise that we approached it with. And ensuring that everything we put into the building had more than one function. And then in terms of efficiency, one, optimize passive systems wherever possible, passive heating, passive cooling, passive ventilation. And then where we did need to add active systems, making sure those active systems did as many things as possible. And so we had indoor plants that were part of the air filtration system rather than an active air filtration system. We had systems for capturing drinking water, both rainwater as well as humidity from the air that was condensed and filtered. We had solar generation and storage. And so really this was intended and designed and built to be able to be kind of dropped anywhere and then fully function in a wide variety of climates and environments. On a practical standpoint, we had 6 weeks to design and build this entire thing. So for any of you complaining about studio deadlines, I don't recommend it. It was not fun, but it was an interesting exercise in what can be accomplished when put under a lot of pressure. And the decision making that kind of falls out of needing to be really crystal clear in both decisions around design as well as construction that all reinforce these sustainable design goals. So we're really excited with how it turned out. But what was, I think, most interesting to us was the way in which we narrowed in on materiality as a really critical element. And so you can see here, there's a common theme in what that building looks like on the inside. And so it was, in essence, looking at natural ecosystem services, photosynthesis, to produce the building to the greatest extent possible. And then on our end, minimal processing to translate those biogenic natural materials into a building that was pleasant and aspirational to be in. And so as a practice, this is a drawing that we continuously keep coming back to. And it's really looking at material classes and how we as designers are kind of responsible for specifying these kind of far afield impacts. And so on the far left, we have these natural materials, grasses, trees, which are generated photosynthetically. And then as we move to the right, we look at an increasingly intensive materials that are extracted, mined, processed, often to achieve really high performance results. It's really difficult to build a window that you can see through out of wood. And so there's a reason that we have glass. It's really difficult to build skyscrapers or foundations out of straw. There's a reason that we have concrete. And so there are kind of technological advantages to these increasingly intensive and disruptive material classes. But as designers, we just need to be cognizant of when we specify or design something that we acknowledge whether there's an alternative that could be ecologically friendly, that could be minimally disruptive, that could be regenerated. And then when we look at carbon, what are the carbon impacts? And so if we look at kind of our 3 buckets of conventional structural materials, we have concrete, steel, and timber. One, recognize that there's a weight difference. Always helpful to understand the tactility of the thing you're building with. And so a metric ton of concrete is very different than a metric ton of timber in terms of volume. But then also looking at this carbon implications for, on the right, mass timber, which is relatively minimally processed, versus concrete or steel, which are essentially global commodities that are intensely processed and have very significant carbon implications. And so if our goal is to design with materials that are storing carbon, then the goal is really, I think for us, quite clear that we need to identify biogenic materials that can lock away carbon. And so really looking at opportunities to turn our buildings from sources of carbon emissions into carbon banks that are durable and store that carbon away for the life of the building. One of the ways that we found ourselves into this as designers and builders, we are a design build firm, and so we do get our hands dirty, is through the construction of mass timber bridges. And so this is a tangent of our practice. I think when I talked about this earlier, maybe I gave the impression that all we do is bridges, but it is a really clear distillation for us of it's pure structure. The architecture is the structure, and the material is exposed. And so it is the highest intensity exposure that we can design, at least in our field, in terms of material performance. And so we were asked a couple of decades ago to design a vehicular bridge for a project. For a variety of reasons, we decided to experiment with glue laminated timber as the actual structure and deck of the vehicular bridge. This is a private client, and so we had some flexibility where to trial some things that were a bit uncommon at the time. And we took basically a relatively off-the-shelf industrial material, turned it on its side, and that became the timber deck. And it worked really well. And then we tried a few more. And so this is a pedestrian bridge. This is going over a very delicate waterway and wetland. And one of the goals was to essentially develop a profile that could be prefabricated, installed on site with minimal equipment. And so we developed these kind of S-shaped glue lam vents, which were all lifted onto a single column, dropped into place, and then fastened together by hand. Some of the benefits, we could actually scribe that to natural ledge and have a lot of control over the way in which that material interfaced with the built environment, with a natural environment. And then also really, we thought it was a kind of blended beautifully into the woodland scene. So those were some early projects that we were developing mass timber. This is well before the rise of mass timber as a real industry, and certainly in terms of code compliance that we see today. We'll talk about that later. But what it allows us to do is to then look at scaling. So one of the themes we keep returning to is, can we find solutions that can be replicated and can be scaled? Because as lovely as it is, a small bespoke pedestrian bridge will not solve global warming. And I don't think there's enough demand for pedestrian bridges, unfortunately, to really move the needle. But it is, again, for us, a really good test of, can we put these material classes into really demanding environments? Can they perform? Can they offer advantages that other material classes couldn't? This is a 135-foot suspension bridge. This is a nonprofit with public access. So the stakes are kind of getting raised here. We're no longer on private land. We're actually dealing with the general public. We have state Department of Transportation becoming involved. And can we find material solutions to bring bio-based materials and actually meet these increasingly stringent demands? And so this was a design that we developed to take advantage, one, of natural outcroppings to minimize excavation, but then also to develop these kind of lightweight glue lam elements that could be essentially hand set along the length of the suspension bridge. So yeah, this is the bridge going in. This is a project where we served as a general contractor, and so we had an unusual level of exposure to a lot of the benefits and challenges of using this material. But it was what we felt was a really successful deployment and of timber in an application that really sees a lot of heavy use. And so this has been now in service now for 12 years. And we visit it often. We have projects all around this. We regularly return, and it's holding up extremely well. And so what this has allowed us to do, because we're operating essentially in a place where we don't really have a lot of literature certainly in the US on mass timber bridges, how do we keep kind of raising the bar to prove that these systems can be adopted at scale. So this quickly is a much larger mass timber bridge that's going over Metro North along the Hudson River just outside New York City. So once you go over a train, things get real. And this is we originally developed with some of our Canadian partners in structural engineering, and it's a glue laminated deck spanning the entire length of the tracks. And so this is a vehicular and pedestrian bridge. It is under construction now. Hopefully we'll wrap up in a couple of years. But again, kind of demonstrating for us and for a variety of state kind of authorities that yes, this is a viable way to rethink how we might otherwise specify infrastructure. You know, their go-to set of details is around reinforced concrete construction. They're tried and true. Why would you ever deviate from something that we built before? And so this is, for us, was an exercise in really making a climate argument, but also proving that this is feasible. This is a project that I shared last year, the Jolliest class. I'll quickly go through it. This was about the same time that Suspension Bridge was being constructed. We were also building a public school, and this is in New Haven, Connecticut. So this was the first public building in the U.S. that had exposed CLT with public funding. And this was kind of a brave new world for a lot of people, but the real advantage we had was that our client was incredible. And so our client was an ecological charter school. It was run by a group of graduates who had most of them had forestry or ecology degrees, and they operated an old farm that they had turned into a school, and it had this kind of lovely menagerie of buildings scattered throughout the landscape. But it was all quite informal, and they were growing, and they needed a building that not only could serve their practical day-to-day needs, to meet the basic programming of being a high school, but one that really embodied the ethos of their curriculum, the ethos of their campus. And so we developed this kind of agrarian form as a roof form that responded to the site and to their identity. But then really quickly looking at how does that roof form serve the building in more ways than simply being kind of an icon or a formal idea. And so layering in the idea of bringing in natural light, very highly insulated envelope, a series of PV arrays that were south-facing, geothermal run out into the landscape, which was then paired with stormwater collection and filtration and treatment. And so, having that idea of the roof do as much work as possible for the school. And then once we had that idea and that operation, looking at, well, what do we build that out of? How do we build this roof in this school in a way that is most aligned to their ethos? And shocker, we used wood. And in particular, because we had the benefit of these really engaged high schoolers. These high schoolers were part of client meetings. They're part of decision-making teams, which is an amazing opportunity, but also kind of wild. You guys were all high schoolers not that long ago. To basically be part of the building committees and have a really active role in it was a really interesting opportunity for us as practitioners. We think it was a valuable opportunity for them. But what we really focused on with them was, well, if we're going to build this building and we want to understand the landscape and we want to understand the ecology, we also want to understand where does this building come from and what are we using in the building. And so we worked with students. We actually tracked all of the different species of primarily of trees that were brought into the building. Where were they harvested from? What age class were they when they were harvested? What different product classes and types were generated from those various harvests? And then when they were deployed within the school, what are the carbon implications? How much carbon are we storing? And really tracking that closely. And again, for us, it was a privilege to be able to kind of do this kind of work through the design process, because this is a feedback loop that we often, as professionals, don't have the opportunity to really investigate. But here, it was a design criteria, and then leveraging prefabrication. So all this was built off-site. It was most of the material was sourced from Quebec, brought down to New Hampshire for fabrication, and then installed on site with 5 carpenters. And so the whole building structure and exoskeleton went up in about 6 weeks. So very exciting for the school population to watch their building go up so quickly. And as a demonstration, again, when we're bringing new materials, products, and assemblies into kind of these more public realms, actually having a successful construction experience is really important to convince that, yes, this is a feasible way that we can change the construction industry. And so here are some photos of the building completed. We're really happy with the building. The students are really happy with the building. But what's really interesting for us is that this isn't just a school building. It's actually a community anchor. And so it serves a wide variety of public functions. It has a garden that is a farmer's market. And it has a large assembly space, which is one of the larger places for gathering and community events in this neighborhood of the city. And so this is visited by 20,000 community residents a year for a whole variety of activities that have nothing to do with the school. But the building is able to sponsor all of these kind of unanticipated uses because of designing for flexibility and change. At the end of this, we were really fortunate to have an experience. We're really happy with the building. It looks great. Everyone enjoys it. And that's usually where the project ends. You might come back, you might bring a tour back in a few years, but really as architects, that really is kind of the handoff. We had the very kind of rare privilege of then being asked to, well, let's look at how we did as designers, kind of check our work. And so we had a grant and through a book project, we were able to really dive into kind of ex post facto analysis of how did we do? We had all these goals as designers that we were going to design ecologically, we were going to design for carbon storage and performance. Did we succeed? And being really critical about it and auditing our own work. And so this is a carbon analysis of the Common Ground High School, and it's looking at all the various subsets of the building, all of the impacts that we can measure and track. And so, this is how we did in terms of the embodied carbon that we're talking about. And everything above the line is an emission. Everything below the line is storage. So if we look at site work, it's not great. We had to take down a lot of trees. We had to move a lot of soil. We had to reconfigure wetlands. So we had a really massive carbon spike. Now, if we hadn't done those things, there was no other place to put the building. So this is the challenge, is that some of these things are difficult to avoid because that is the premise for the project, and the benefits might outweigh the cost. Looking at foundations, again, no surprise, they're concrete. They're going to emit. We talked about earlier in the graduate seminar some interesting graduate theses looking at wood. If anyone wants to look at some wood-based foundations, we're all there for you. But there are some realities of the appropriate material and the appropriate application, and that's the foundations in this case. Now they are smaller because it's a lighter building than would have been for a steel building, which was the preferred alternative by the state. So we were able to decrease this, but still, it's an emission. Then we get into all of the wooden elements, so the prefabricated frame, and the facade, and the decks, and the roof. And so these are all really amazing carbon storage opportunities. They're all built out of wood. They're minimally processed. They're relatively regional, so we didn't have that much transportation. And so this is really where we were able to leverage a significant amount of stored carbon into the building. Some miscellaneous doors, stairs, not big drivers. But again, the kind of the elephant in the room are the mechanical systems. And so this was designed to be a really highly sustainable building, ground source heat pumps, PV arrays, all the bells and whistles that we as designers felt were appropriate for a school with this kind of focus. There's no carbon storage in wiring. There's no carbon storage in your heat pump. And so it was a massive spike just to heat, cool, and light the building. And again, some of that's necessary. But I think now that we have we've been able to do this audit, it really did raise questions for us about the efficiency, the distance of which we laid out lighting. Where do we locate particular elements of the building systems package? It's a huge spike that I think we in the future are being much more conscious about trying to avoid. And so we look at, this is the very famous Stewart Brand shearing diagram that looks at these various ways in which the building sheds and changes, and in some cases stays static over the course of the building. So the The darker lines are those elements which are more permanent once they're installed. The lighter lines are things that are changed out more rapidly. And so for us, we are really focused on those big sunk costs. And so the structure, the site, the skin, the things that are least likely to change over the life of the building. And then where we can influence fit, finish, and materials that might circulate at a more rapid rate. And so if we are looking at structure and we are looking at carbon storage, we're looking right now primarily mostly at timber. There are a whole host of other material classes that are emergent, that are also bio and biome based, which are really exciting. But for now, the most ready at hand solution that we have is building with timber. And so what that means is that designers, we need to understand that material class. And again, I think I'm preaching a little bit to the choir, given some of the conversations I've had earlier today. I would say the exposure that you have broadly to this topic is a little bit different than the schools in the US, let's put it simply. But when we look at traditional ways in which we talk about timber, we're talking about, taking a large diameter tree, we're felling it, and we're processing it. So this is how the industry started, is extracting the largest thing that we can find, and then subdividing that into smaller and smaller elements because it's easier to ship that way. And so the kind of perverse and I mean kind of shocking reality of the wood industry in North America is based on these practices. And the reality of extracting these resources informed supply chains. It informed the way in which those materials are measured, standardized, shipped. It informed construction details that are still visible and utilized in some cases today. This is mill construction, very similar to what I've seen here in Cambridge. It informed the way we think about risk for fire. In some cases, in particular around fire risk. This is for those of you not familiar with this image. This is from the San Francisco earthquake, where the mill building caught on fire. The old growth heavy timber beam charred and stayed intact. The steel catastrophically failed, turned into spaghetti, and draped across it. So there are these certain advantages of building with timber that we've baked into our codes, baked into the way in which we understand it as a material, and in the ways in which we've deployed it into, let's say, lower density construction that really, unfortunately, hasn't changed much in 100 years. So this could have been taken 100 years ago, could have been taken yesterday. Difficult to tell, unfortunately. The significant evolution that we have as a technology with wood is around finger jointing. So the ability to machine and join together individual boards, lamella, into these longer and more predictable building elements. And so, for broadly 100 years, we've had dowel laminated, nail laminated, and glue laminated timber. It's not been adopted at a massive scale. It's certainly not enough to inflect new ways of building writ large, but that really changed with the evolution of cross-laminated timber in the 90s. And that as a material class began to compete with concrete and steel in terms of its two-way span capacity. But really from the architectural perspective, it began to change the morphologies of construction. And it allowed us to move away from kind of conventional post and beam single span decking that we're also familiar with to all of these new inventive kind of homogeneous material systems that take advantage of these large scale prefabricated elements. And so what does that mean? That make different things? Sure. But what it really means is that from a code perspective, and this is what I'm getting back to, something that can be adopted and built at scale, is that we all of a sudden go from a 6-story building maximum with wood to 18 stories. And so this is a change in the IBC in the US. I know that Canada has a kind of parallel adoption, is that in the span of 10 years, building with wood has gone from a novelty that was for institutional buildings, and that was typically utilized only for single family construction, to now something that is regularly competing economically with steel and concrete for mid and even high rise construction. And not only has the industry changed to support that, but the codes have changed. And so I know that maybe the duration of time in this room, so for some of the students here, might be difficult to appreciate that. But the last time we had a change like this was when steel was kind of incorporated into the building codes. And so right now is a really dramatic time in how we have opportunities to utilize biomaterials in a way that 10 years ago would have been, frankly, a fantasy. And what does that mean? So when we began to build more densely with wood, we're able to shift from lower density, lower value construction that tends to take up a lot of space, both in terms of its footprint as well as its infrastructure, to higher, denser aggregations of timber buildings. So we're storing more carbon per area. And then when we look at zoning, land use, all of a sudden we're pivoting from this dispersed, disaggregated, and low density construction to really durable, dense aggregations of carbon in the built environment. And so these are all mechanisms of policy that are kind of unleashing the potential for the built environment to be a carbon storage machine. And then when we look at this relationship between forest landscapes and the built environment, if we're managing our forest right, if we're harvesting them regeneratively, and if we're developing value-added products out of those forests, kind of to the highest and best use of those individual species or trees, then we can deploy those into appropriately scaled buildings and infrastructure such that we're banking carbon in the built environment, and we're ensuring that we have stable carbon in these further afield natural landscapes. So I'll show how we're trying to put this into action on more replicable projects as a practice. And so this is an aerial. This is in New Haven. So this is our office. This is an old industrial neighborhood in the center of New Haven, and we have had the very privileged opportunity to work on mass timber buildings on either side of our office. I wish this was a replicable business plan for everyone in here. We just got lucky. And so I'll talk through these two. So first on the left is Firehouse 12, which is a single-story mass timber addition onto an unreinforced historic firehouse. And then on the right is a much more intensive mass timber addition onto an unreinforced masonry warehouse. And so for the Firehouse project, this is a project that, again, we feel very fortunate to be a part of. It's a projects that we have been involved with over the past 20 years. The first one was built in 2006 when we began an adaptive reuse of this vacant firehouse, and we have iteratively gone back to this project many times. And so on the ground level, you have a bar and a restaurant. On the second level, we have a jazz recording studio and performance space. Above that is an apartment, which was mostly a kind of a recovery and exposure of some of the original building materials and preserving that. But then I think the part that I really want to focus on is the addition, which was the small mass timber 3-bedroom apartment that was added on top. And so this is kind of functioning as it's a very unique program section. Probably not that replicable, but the impetus was that they basically ran out of room, and so the success of the jazz studio and the restaurant and having musicians come and record here, such that they needed more space. Certainly didn't want to demolish the building, and so how do we add space to an existing building? We go up, and in this case, it was an unreinforced building, and the only material that we had at our disposal that couldn't have the strength weight ratios, that had the stiffness requirements, that wouldn't then require us to go back and undo all the work we'd done in the lower 3 levels was a mass timber box. And so we developed this is an all CLT project that was dropped into place over the course of a day. It has a CLT core, a circulation core that ties down into the existing unreinforced masonry. And then as you move up into the living area, it is black spruce CLT as your floor structure and finish, black spruce glulam as your lateral reinforcing systems on the wall and your finish, and the ceiling, which is black spruce CLT as your ceiling. So this is an unusual project for kind of really living in a mass timber building. But we felt it was a really successful experiment in showing the capacity for these basically industrial products. All of those wood panels are typically used for industrial decking. You put it through a thickness planer, it looks great. So we're really trying to use these which are kind of off-the-shelf materials and bring them to kind of their highest and best use in a way that exposes and celebrates them. More recently, we've just now finished Acme Timber Lofts on the other side of our office. So this is a view of the street from a few years ago. This was a really densely populated area at the time. There's been a lot of demolition, adaptive reuse, but the building that we were working within, it had party walls on the two sides. It had a party wall in the rear, and it was directly on the street on the front. So it was basically completely landlocked. And so the challenge was, well, how do we basically convert this warehouse into residential units? How do we do it in a way that adds density? And how do we do it in a way that preserves as much of the existing building as possible, so that we're not having to rebuild something that already exists? And so this is the main mechanism, which is the stair and elevator core. So this is an all CLT stair and elevator core. It is, to the best of my knowledge, the tallest CLT elevator shaft in the world. And not only that, but it was actually inserted into the existing building. And so this was the existing warehouse. We stripped the top attic off to create a level surface. And then a very brave crane operator dropped in the panels blind over the unreinforced masonry wall and into the elevator shaft. And so that is how the building basically anchors down into the new foundations. It preserved all the existing exterior walls. We didn't have to demolish or do a seismic retrofit. And so this was a very efficient way from a structural perspective to add additional height. And then the entire assembly, all CLT. Pairing that with on the left, adaptive retrofit of the existing very poor performing masonry walls, bringing those up to passive house standards, and then on the right, utilizing new passive house details for the exterior envelope. So these are the finished units. People started moving in there last week, I believe, and so we're very excited that this is now being lived in and enjoyed by new tenants. But this brings us to kind of like the next phase of how we as a practice want to bring these down to the world. And so it's not just enough to build these very specialized bespoke buildings for market rate renters, but how do we bring these to deeply affordable communities who don't typically have access to, let's say high design, natural materials, high performance buildings. So this is a deeply affordable project. It's an infill site on a brownfield and also in New Haven. This is designed to basically replicate all of the same fit and finish that we saw in those previously two projects, but do it at a construction cost and that is acceptable for deep affordable housing. So this is a publicly funded project, and it has 69 residential units over 2 buildings. And the goal again was to basically take those same design approaches and bring them to a class of buildings that typically don't see that much innovation in terms of the way in which they're built. Where we had some challenges, so we designed in kind of an all bio-based assembly, very ambitious, all wood finishes, exterior insulation was wood fiber, exterior cladding was treated wood. Difficult to get that to pass some of the agency requirements. And also, I won't get too far into this because you guys don't have to worry about it yet, but procurement is another challenging issue with bio-based materials. But basically, how do we design systems that are flexible enough to accommodate all of the various changes and options that we have in a bio-based industrial supply chain rather than very commodity-based extractive materials? So the building strategy here was essentially all CLT, with the exception of a little bit of steel for the parking. All single source from one supplier that ended up being out of Austria, shipped directly to the port of New Haven, and then some pictures of it under construction. So we have the first residents moved in 2 weeks ago. So they're doing the move in right now. Again, we're very excited about the potential of this to show kind of an alternate scenario, an alternate future for what housing might look like at a really affordable price point, and for a population that really deserves the best design that we can bring. I'm going to quickly go through. We have some other residential projects. Again, this is all about bringing these to scale. So these are some other projects in our pipeline that we're kind of learning these lessons. The projects are getting bigger. They're getting more, I would say, replicable. and they're creating more of an impact. And so this is our kind of my final multifamily slide, is that this is a new district in Burlington, Vermont, just over the border. And so this is 13 acres of new construction. All of it, again, from the premise, is on a brownfield site and is designed to be passive house and bio-based material. And so this is an amazing opportunity for us to be involved at the outset with a development team, a construction team, a city design team, that everyone is kind of pulling on the same oars and wanting to make the building not only fit into kind of an industrial landscape, but really embedding all these things we talked about for performance, materials, carbon storage, carbon sequestration from the outset of the building's life. So this is going through entitlement reviews right now. A short aside, this is also in a bit of a criticism on the double loaded corridor. So it's all accessed via exterior corridor. It's a bit unusual for a climate like Vermont, certainly not too dissimilar than here. But this is part of questioning what the status quo is. Do we need a condition 5 feet by 100 feet of space that you're only using to move from the elevator to your apartment, or can we build that as unconditioned space that becomes an amenity in a community space? So we're saving cost, we're creating more efficiency, we're also creating more community, and in our opinion, maybe a more lively design. So I think these are some of the opportunities that we have designers to question what we assume are the givens and the norms in the market, and provide alternatives that are compelling. And then as we do that, through the development of buildings, building assemblies, building designs, working with biomaterials, we need to really also familiarize ourselves with the reality of working with wood. If that's the path that we choose to a strategy for decarbonization, is to recognize that this material has a lot of flaws. There's a reason why this is not the baseline assumption for new construction, certainly in urban centers. It has challenges that make it difficult to engineer as compared to the commodity products of manufactured steel and concrete. But what we can also recognize is that it has a whole host of benefits. And as long as we are designing with those benefits in mind, that can overcome the perceived challenges of certainly timber, but I would apply this to all bio-based materials that are more heterogeneous than our kind of manufactured extracted product classes. We also have to be literate in questions about landscape. And so oftentimes when we talk about mass timber, one of the first questions we get is, what about the forest? This is what happens to the forest. If you want to make timber, this is what happens to the forest. That is true. There are disturbances to harvest that timber. But in reality, if this is managed well, this can be regenerative. In contrast, land conversion is much difficult to undo. You're not replanting forest where you've converted it to an entirely different ecological use. If you're now using it for inhabitation, you're not using it for growth. And even disturbance. I mean, again, I think I'm preaching to the choir here in Canada, but the reality of extreme disturbances is only getting more intense. And should we be cutting down forests to produce buildings? This is a study that we're really excited to be a part of. This is a study at Yale Applied Science Synthesis Program, which looked at the perception that if we leave our forests alone, as maybe some would advocate we do, wouldn't that be better? Wouldn't that be a better and more resilient way to store carbon, is to leave these natural landscapes to be natural? And so they charted out, sure, this is if you never cut a forest, if there's no disturbance, you will over time accrue carbon storage because your forests are growing. But that's unfortunately not the reality we're in. The reality we're in now is that we're in a period of extreme disturbance. And this is the baseline. So whether this is fire, this is pests, the forests are less resilient than they used to be. And if left unmanaged, will only become less resilient. And so this is a really fundamental shift in how we think about protecting our forest landscapes, is that actually by managing them, by designing for regenerative harvests and regenerative cutting, we are not only adding value to those landscapes, but we are protecting them by taking that carbon that may have otherwise been lost and locking it away into durable building products. And so this isn't to say discriminately cut forests, make as much Kleenex as you want. This is to say be really intelligent and really thoughtful about how we utilize the forests and put it into elements and buildings that are going to lock away that carbon for a long duration of time. So as designers, How do we do that? That's a lot to talk about. There's a lot of different ways that we may have agency, but we're a relatively small number of people in a very large kind of construction sector. And so, what are some opportunities that we have ready at hand to begin to decarbonize our design? So first is just simplify. So simplify the volume, simplify the complexity of the building to reduce the number of layers, number of trades, number of machining, reduce the weight. So weight is usually commensurate with transportation and carbon emission cost. So can you make a lighter building that is easier to build and easier to handle by the people actually on the site? Can you minimize disturbance both on the site where you're actually building the building, but also in the remote landscapes where those elements, materials, and minerals are coming from? Can you take advantage of ecosystem services? If rather than manufacturing a product, can it be grown? Can it be grown naturally? Does it have to be farmed or harvested? So really looking at the opportunities that we have that are naturally occurring that can be leveraged into the building design. Reuse materials, designed for a durable building that can be flexible and at the end of the day disassembled and have a secondary or tertiary life after we're done. Keep track of where the materials are coming from and how they're getting to the site and where they're going afterwards. The time and distance has massive implications on carbon footprint, and share resources. So this means not only share space, but share infrastructure, share energy. Can you kind of reconfigure the program of buildings so that they are doing more with others? Store carbon, obviously, and then finally decouple. So decouple the idea of economic growth from resource extraction. Decouple the idea of aesthetic beauty and merit-based design from precious materials that are difficult to regenerate. And so that's a mental decoupling that we as an industry really need to focus on. I'll quickly wrap up with a few examples of how we in our practice have tried to implement those strategies and three very different building types. And so here, this is a research station that we designed and we're actually the builder for. This is on an island in the Long Island Sound off the coast of Connecticut. It is an island that's owned by Yale University as an ecological research station. And we were asked to build a building for the researchers who visit the site. In terms of impact, it is the entire premise of the island is that it is as natural as can be possible. There's no electricity, no running water, no sewage, no transportation. It is a rock in the Long Island Sound with a very small dock. And so where we site the building has a really profound implication on the rest of the island, and not only on that ecology, but also on how how durable that is. In terms of the building, it had to do everything. It's similar to the project for the United Nations, where the building had to be its own infrastructure, energy generation, water capture, treatment, sewage, you name it. The building had to carry all of that. And on top of that, be bio-based. So not only bio-based material wherever possible, but actually harvesting material from the site. And so when we had to clear the site, finding ways to take those trees and reincorporate them into the structure and into the finish. Again, very fortunate to have a client, in this case, the Peabody Museum at Yale, that wanted to challenge us on those and really push and be with us in pushing those topics. So we worked with grad students at Yale. They designed it with us. They built it with us. We prefabricated the entire building, rehearsed all the assembly and disassembly, packaged up those materials. This was our COVID project. So no place better to be than an island in the middle of COVID. And then shipping it to site, which was, I think the correct term is terrifying, to watch your building being plucked off of a barge by a very precariously placed set of equipment in a skid steer that on this picture is just about to fall into the water. And also questioning, yes, we can make a really big panel, but what does it mean to move it? How heavy is that? Once in this case, once the skid steer lifted it, the students had to move it by hand to the building site. And so really, these are questions about weight, dimension that are really embodied dimensions that we have to kind of think about as designers. Like I said, we harvested material from the site. So this is sassafras that grew on the island that was then repurposed and turned into the vertical structure. So the material actually never left the island. We did all the processing on site. And then this is the end result. So this is the research station, again, kind of fully off grid, fully self-sustaining. And it's a pretty simple program. It's a big open space that can be closed down in case of inclement weather. It has natural finishes, and then it has sleeping berths for researchers who want to stay on the island for kind of a longer duration research. And then, again, from a ecological perspective, it kind of disappears, which is the goal. We didn't really want it to be that visible. So the over time, it has really receded into the background. At the other end of the scale, and at the other end of the globe, we have found ourselves in a very interesting position to be advisors to the King of Bhutan for a reconsideration of how their construction sector operates. This is a much longer conversation than I have time for now, but it has a lot of the same principles. It is a beautiful natural landscape that has really stringent environmental protections. It has a very alive cultural identity in terms of its built environment. So these are practices that are actively passed down within craftspeople that are still alive today. But it's also the fastest urbanizing country in Asia. It has a massive shift of population from alpine villages down into slightly more temperate river valleys. And with that, a really significant increase in construction methodologies, which are often misaligned with, I would say, the cultural goals of the country. All of the material in this, except for the bamboo, actually maybe even the bamboo, is imported. The labor is mostly all imported. There is very little in terms of a construction industry in Bhutan. And so this is not only a significant drag on the GDP, but a huge source of carbon emissions because 99% of construction is reinforced concrete. And so we were asked as part of a much broader team to, well, are there alternatives to rethink how the country, which is, for those of you maybe unfamiliar with this part of the world, to the north is Tibet, China, to the south is India. So this is a very small landlocked country between two very different scaled economies and populations. But how can this country really look at domestic opportunities for sourcing and industry, take advantage of long-standing forest management practices that have developed a range of what's called FMUs, or forest management units, across the mid-belt of the country that are currently really well managed, but often misaligned to how those, where are those forests being utilized? So a lot of times it's going to firewood, it's going to kind of low-value furnishings and finishes. So how can we redeploy wood that's already being harvested and develop a set of tectonics that are more appropriate to the demand that they're expecting, as well as the cultural needs of the country? We're also looking to develop kind of a specific approach to manufacturing that you typically would not see in, say, North America or Europe. To find an acre of flat land in Bhutan is very difficult. And so how do you rethink manufacturing at scale when you don't have anywhere to put things? When your longest truck is only 14 meters, when you only have a handful of cranes for the entire country. So these are logistical questions that really inflect the way in which we think about industrial processes and the way in which these buildings go together. And so looking at smaller modules that are easily shipped, that can be lifted in place by hand, that are compatible with the finishes, the construction aesthetics of the country, that can host a very diverse range of programs, which again is a whole other conversation about mixed use programming. Bhutan is an incredible example of stacking disparate programs in occupations every which way. It's really an exciting place to be. But then also, so taking that structural system and then adopting maybe aesthetics that we aren't projecting. It's able to absorb very specific cultural ideas about what is appropriate. So we're solving a technical issue, but we're also facilitating the preservation of a culture and producing interior spaces that we would think are really desirable and really resonate with the identity of the country. But finally, just to bring it back a little closer to home, so this is the Northeast Forest, the U.S., southeast of Canada. I don't know. Northeast Canada is a very different place than Northeast U.S. But these are our mixed species forest. Not too dissimilar. I apologize for leaving Cambridge off the map, but I assume quite similar in terms of forest stands, that we have this really heterogeneous mix of forest types. It is changing rapidly. It is climate change isn't helping. And it has a really dynamic stand succession, which is different than what we would find in the boreal forest, certainly, or in the Pacific Northwest, or even in the US Southeast. So it's a really dynamic system, and that's paired with really large demand centers. So again, I apologize for leaving Toronto off, but we have New York, Boston as really significant urban drivers of demand, paired with these large wood baskets of heterogeneous forest species and forest types. And how do you develop an urbanization strategy that can take advantage of all of this disparate material that currently isn't really utilized in the building sector? You know, in the Northeast, when we're building mass timber buildings, it's coming from the US Southeast, very rarely from the Pacific Northwest, but mostly from Europe and from Quebec. And so how do we re-localize some of those supply chains that actually take advantage of the mixed species and mixed stands that we have? And so this is a project that our office has been developing along with our partners at Yale with support from the US Forest Service. And it's looking at a whole variety of ways in which you can take a lot of different species and mechanically attach them to create these high performance, long spanning elements to replace, let's say, conventional mass timber, which is usually a mono species. And so this is a long-term project of kind of looking at dense construction that can absorb flows from the forest rather than specifying a single species or a single manufacturer. And how do we create these dynamic assemblies that have better performance than we may otherwise achieve with a conventional monolithic material? We really are interested in non-adhesive based solutions, non-metal based solutions. And so we had a whole kind of rabbit hole we went down on timber fasteners as a means to actually achieve these long spans. Testing these things in our own shop to determine how they perform relative to conventional assemblies, and then also developing all the manufacturing and fabrication techniques, because these are things that simply just aren't being asked right now by industry. That's more focused on creating really efficient rectangles to ship out all over the world. You know, how do we create post-processing opportunities that can be decentralized, deaggregated, and require very low CapEx requirements? So for any robotics folks, we can dive into why that's really complicated later. But what it produced for us was this idea of a cassette which could absorb multiple types of wood species and stand classes, and then pairing that with mechanically laminated beams and columns, again, all mixed species, to produce these really dense and flexible urban assemblies. And so this is a full-scale prototype that we've now built, a bay of this. We're going for more testing on this. This is, but for us as a practice, is a really interesting moment to kind of be paired with industry and rethinking how the future of the built environment can really develop in a way that is architect and designer led, rather than architects simply just being the specifiers of systems. Can we lead in the rethinking of what those systems might be and what are the processes involved in them? And so this is, looking at these like large, long span, flexible building types that could be office, it could be educational spaces, they could be residential spaces, but it's really a kind of a carbon storing framework that is really resilient and durable for the life of the building. So why does this all matter? This all matters because we are collectively building along a carbon transect. And for hundreds of millions of years before we got involved, carbon drawdown was happening through natural biogenic mechanisms. So we were creating these geological locked pools of carbon, which, of course, we discovered that you could then dig up and burn, handy for us. And in so doing, create massive amount of carbon emissions, basically undoing hundreds of millions of years of carbon storage. And so we find ourselves in this carbon present of, are we at a peak of this practice? Can we rethink different ways of operating and of kind of developing the built environment? And can those methodologies and practices that we as designers can bring into the world, can they begin to draw down and store that carbon back into the earth and out of the atmosphere? So I'll leave it there. I think I talked too long, but I'm happy to take any questions.
Thank you. So we'll take about 20 minutes for Q&A. Can we just jump right in?
Sure.
Okay.
Hello, my name is Makaya. I'm a 2A student. I just want to say first off that your diagrams were like really well done and they're beautiful. And I definitely respect the amount of time and effort it takes to make those drawings legible and for us to understand because we had to do it for our studio this semester. My question relates to the shippable homes that you mentioned that they were about a 6-week turnaround.
Yeah.
I was wondering if you saw those as a solution for that disaster relief. It came to mind because Hurricane the Melissa, I believe, is happening right now, and it's causing a lot of havoc. And
Sure.
that would maybe solve some of those solutions with rebuilding some of the housing that is lost. So I just want to hear your position.
Yeah, thank you. And thank you for the diagram appreciation. Yeah, I think the premise that the UN approached us with was really born out of a real acute need, and one that unfortunately is not yet solved, of that the reality that we have an increasing number of these disastrous weather events, for lack of a better term, that create mass displacement. And the challenge is that it's, we can't look at a schedule 5 years out and say, oh, well, we know that Haiti is really going to need a lot of housing in 5 years. These are things that they have to be responsive to almost in lifetime. And so the premise that they had was that is there a scenario by which they could essentially stockpile these minimum dwelling units in areas that they knew generally would be subject to acute needs for housing, and then deploy those as needed in the event of an emergency. So that was the premise they came to us with. Since and the UN has not really taken that up as a model. They have other things that they're focused on at the moment. But there have been some other kind of nonprofits that we've worked with who have similar goals and ideas, and that we've collaborated with them. We haven't seen that system developed in a way. And I think this goes to, I think, a broader question in our mind now is what's an appropriate way to prepare regions for those events, and is it to have these kind of volumetric, ready to go houses sitting on parking lots, or is there more of like a flat pack core that can be sent out that is more stackable? The question that you quickly get into on the question, this issue of prefabrication is space, and so again, not maybe something that is experienced in school, but understanding the reality of kind of when we design something that can be prefabricated, we then have to design 2 or 3x amount of space to actually move around it, to store it, to ship it, to handle it. And when that gets deployed at scale, so we're talking for that project, we were talking thousands of units, and the spatial impact of those decisions is really enormous. And so I think one of the questions that we have, and we haven't been asked to to build more of them, is there a more space efficient solution that could be kind of warehoused in a way that then could maybe sponsor self-build, or maybe there's an intermediate idea about having softer materials. And I think there's a whole interesting kind of constellation of other people beyond us that are looking at disaster relief and housing needs, and finding ways where we can kind of intelligently build things that are, unfortunately, will have to be durable, because the shocking reality of what we learned working with the UN was the duration to which a lot of these ostensibly temporary solutions actually become permanent settlements in disaster relief zones. And so I think that is the idea of when we put something out into the world, as a temporary solution. In reality, that may be absorbed as a permanent development. And what's the most responsible way for us to design and build that?
Hi, I'm M1 student. I also really enjoyed all your diagrams and drawings. I thought they were really nice. I was just wondering about the 340 and Dixwell project. You said you got your wood from Austria.
Mhm.
So how does that affect the overall carbon impact of that project if it's from such a far away location? And why did you not go with a more local?
Excellent question. So on carbon impact, transportation via sea is actually quite efficient. So the Port of New Haven is a break bulk port, and so we were able to offload that material 1 mile from the building site. So that is a very different narrative than if we were bringing it to, let's say, the Port of New York and then moving that material up to northern upstate New York. So we had very minimal material handling on the receiving side. So that kept the carbon emissions quite low. Fortunately, that wouldn't always be the case though, and certainly the more local options, the better, in our opinion. We, as part of the design process and the procurement process, so this is a publicly funded project, and in the U.S. for public housing, what you can't have is a prescriptive solution, and so we can't design a system that only one supplier can satisfy. This is less an issue for, let's say, concrete or steel or even stick frame buildings, because if a manufacturer of 2x4s is underbid by another manufacturer of 2x4s, then you still have 2x4s. But with mass timber, every manufacturer is different, every species is different. And so the design, basically, we had to look at the constellation of potential suppliers. And so in this case, it was the Eastern US, Eastern portion of Canada, as well as Europe, identify every potential bidder, design for all of those systems, and prove that all of those different dimensions and thicknesses would work, and then put it out to bid. And at the time when we put this out to bid was right towards the tail end of COVID, when softwood lumber prices in North America had quadrupled. And so unfortunately, all the domestic suppliers that we thought we were going to work with were dramatically underbid at that point in time by Europeans who did not have a kind of a corollary massive spike in input costs. And so that's the kind of the reality of this, is that philosophically, absolutely, we would have loved to basically have the material come from as close as possible. But in order to actually build the building and actually have it meet the regulatory requirements of procurement, we had to be open to less ideal solutions.
Hello, my name is Izzy. I'm an M1 student. I was just curious about like how confident or hopeful you are that we will actually meet our like carbon benchmarking, or if you do think it'll just be business as usual. And like, yeah, I'm just wondering what your take was, because it's easy to get really lost and doubtful in the state of things.
Yeah, I mean, coming from the US, that is a pervasive feeling at the moment. Not to put a too fine a point on it. Yeah, I think the reality is that it's not looking great. I mean, that's the candid reality. If anyone was following the COP30 announcements over the past couple of days, a lot of reports were coming out that kind of show the state of where we are and what's the projection of what's to come, and it's pretty dire. I mean, that's just the cold hard truth. I think the thing that I take solace in is that I happen to be involved in an industry which has a significantly outsized influence on how the shape of the future is going to look in terms of carbon emissions. I think we all do, for those in this room. And we have not only a responsibility, but an agency to make active decisions that will have significant payoffs kind of if we make decisions now. And so I think what we take away from the doom and gloom is that we are informed, we have ready at hand strategies that weren't available to us even 5 years ago in many cases, and that we can deploy those at scale very rapidly. And so it is interesting and exciting to be at a stage in history where we do have carbon storing materials readily available to the built environment for buildings of scale, and that, you know, as opposed to some of our earlier mass timber projects, which took years and years and years and years of trying to convince code officials and regulatory agencies of the merits of this approach. Now, not only is it accepted and regulated, but in a lot of cases, what we're finding in the Northeast US is that mass timber is even the cheapest way to build. And so again, we're seeing a really rapid sea change in how the building sector is reorganizing itself around these material classes. And I think the responsibility is for us as designers is to look at, okay, well, great, let's do that. And then what's next? What else can this shift to mass timber production and adoption of biogenic materials? What else can we kind of ride on the coattails of that? So we can look at insulation systems that are bio-based. We can look at finishes. We can look at all of these other ways in which the building itself can be simplified, made more efficient, and made to store carbon. Now that we've been able to solve one of the really significant kind of carbon demands within the building.
Thank you. Hello, I'm a 1A student. First off, I'd also like to share appreciation for your diagrams, especially at the scale that they're drawn at. I think they're really beautiful and legible. I noticed that I was really fascinated by how a lot of the exterior cladding was made entirely out of mass timber. And I was wondering how the timber was treated to become climate resistant and if there's any carbon costs associated with the chemicals needed to do that.
So that is the downside of showing construction photos, is that there are things that happen to those mass timber buildings after those photos are taken. So there are some instances where we do have exposed mass timber. And so the bridges are an example of that, where it's kind of the pure material is exposed for the duration of the building. Some smaller building types are using mass timber and other engineered timber products in the cladding. But one of the challenges that we have, again, to speak kind of to the regulatory framework, is that when we get to bigger buildings, there are significant increases in fire resistance and non-combustibility requirements for the facades. And so that is a lot of work has been done in the past really 10, 15 years on various types of modifications, whether that's acetylation, thermal modification for relatively low-grade timber to become really robust and durable cladding systems. A lot of those cladding systems are not available to buildings above 5 stories. And so as we look to denser, taller urban buildings, unfortunately, one of the hurdles is that we don't, as of yet, have a lot of non-combustible solutions that are also bio-based. There's some interesting work being done right now with straw that has a natural silica content that can produce some very fire-resistant exterior assemblies. But a lot of times wood is kind of best kept to the inside.
Last question. Thanks so much. I learned so much today. I teach housing studios, and I'm often interested in thinking about timber. And then I wonder if all buildings can be built out of timber. I'm kind of interested in your, you brought a number of big numbers. Like we have a big problem. We have to build a lot of buildings, a lot of square meters. And then you talked about how forests do better when they're actually harvested. But they may do better, but it still doesn't explain how much we have to take out of the forest and how much forest exists.
Yep.
And the kind of modeling around. I guess I'm curious about that. Like, build all our buildings out of the forest that exists. And what even about the industry and what about the costs? Like, you said softwood is, at the moment, it seems a little cheaper, but as demand increases, what happens?
Sure.
I guess I'm interested in that kind of future modeling and how much we can.
Well, I don't think anyone is able to throw concrete steel out the window yet. We still need them for certain things. I think the reality is there's kind of two proportions. So one is, what is the relative rate of biomaterial use right now? And so, and where is that use most in demand? So China is a massive demand site right now. It's like 6x the construction of the US at the moment. Over the past 20 years, their use of biomaterials went from 4% of all construction materials down to 0.1%. So we're starting from a very low point for a lot of economies that biomaterials are simply not part of the palette at all. I think in US, in Canada, parts of Europe, that's changing, but it's still an incredibly small portion. And so the capacity for the construction sector to shift that quickly is challenging. It's not known for being very nimble. And so it's a question, is there going to be enough financial and environmental incentive and urgency to make those types of changes? On the sourcing side, one of our collaborators in forestry, Mark Wishney, has this saying that I always come back to. He says, the danger of mass timber as a climate solution is twofold. On the one hand, it won't grow fast enough to make a difference. On the other hand, it'll grow so fast that it'll simply reenact all of the lessons that we didn't learn from the extractive mineral economies. It will basically just, it's a same play, different place. And so those are the kind of the tensions that we're trying to hold in simultaneously. But the reality is that the amount of mass timber relative to timber harvest right now is minuscule. I'm not even sure it's 1% yet. And so it's not only a question of redirecting forest flows from lower value products, but it's also encouraging management of forests that currently aren't managed. And so globally, there is absolutely capacity to absorb all of the vast majority of new construction. The two challenges are, is the construction sector able to make that pivot? And then also the asymmetry between where that wood is located and where the demand sites are really going to be. The boreal forests of Russia and Canada are a little bit further afield from sub-Saharan Africa. Most of urban growth is going to be after Asia. And so that's one of the geographic dissonance that is a real challenge. I don't have an answer for, but the alternative to keep building with concrete, steel, masonry as our primary structure is going to rapidly destroy the carbon budget for the globe.
I think this is probably a good place to stop.
On that happy note.
On the happy note. And thanks so much for being with us and for the seminar this afternoon and for helping wrap up this lecture series. Thank you.
Thanks for having me.